Uncle Alistair, if you can please explain to us what you've done here.
Right. Here we start off, and if you look at the beginning, you will see that you have got a very steep gradient, 1 in 46, and it gradually gets flatter and flatter and flatter and flatter, and eventually it's only 1 in 228. If we look at this 1 in 146, that water is going at 3.38 meters a second, which is faster than you walk.
What speed does a human walk at?
About half that.
Can I just backtrack, Uncle Alistair? Sorry. Guys, this is for the DN 650 millimeter pipe that we're rehabilitating that's conveying oranges. So, Uncle Alistair's...
And what's important about this is that if we look at these high velocities here, where it's going at 3.3 something meters per second, that's what you call subcritical flow. So it's like if you look at a river that's going down in flood, you see waves down the center of the river. And that's exactly what's happening here. So those oranges are being bounced all over the place.
And then
when you get to this last section where it's flatter, then you've got a nice smooth flow. So those oranges basically will be flowing in a straight line. So in this top section, the oranges can get damaged. In this bottom section, they don't get damaged.
So what we're trying to avoid is collisions of the oranges.
Yes, and if you've then got any sort of things like the joints on this are these joints, so that upsets the flow of the water. So you then have little shock waves that are being bounced to the left and to the right and to the left and to the right. Each time there is a little obstruction, and those shock waves then interfere with each other. So this means that the oranges bump into each other and then bump into the wall. So it's almost like if you're playing, on pool table.
Yes, and
the pool balls
bounces against the side cushion of the pool table.
And you've just got a whole lot of these things, and because the water's flowing all the time, you've just got this happening continuously.
So we lining this old concrete pipe with a PVC liner, and I was concerned we're definitely going to increase the velocity. There's no doubt about it.
It's not going to have these bumps at the side. So you're then going to have a more, even though it's going that fast, you're going to have a more smooth flow. But then when you get to the end over here, then there's going to be a problem over there. And that we can't resolve. That the owner has to say if he wants to do something about that.
Because you've written a little C, and that's for critical,
That's what they call a critical velocity. So ideally, what you want to have is that water is not flowing faster than that critical velocity.
Of 1.95 meters per second.
And ideally, if you're designing, say, like a sewer, and you're doing it properly, then you have that critical, you have the velocity at about 0.8 of that critical. So then you prevent the waves forming on the surface, and you've got nice smooth flow.
And over here you were drawing...
And this is what happens if you now have a channel and you have an obstruction in the channel, like a dam wall. Then the water dams up behind it and it flows slowly, and then when it goes over that crest, it accelerates, and then you will see downstream you will have a whole lot of turbulence. So this is what's called subcritical flow, this is what's called supercritical flow, and when you go over this bump you have a constant depth, and that's where you can measure the depth of that, and you can get the velocity, and then you can get the discharge. So that's like a control point on the system.
And if you were designing this as a sewer pipe, would you have the same principle, whether we got oranges transported in it?
And that's why there's so many of the jobs that you've looked at where the designer has not considered the impact of changing the gradients, because you have a higher velocity here and you can say transport a 30 millimeter stone, and then you have a low velocity here and you can only transport a 5 millimeter stone. So if you're transporting those 30 millimeter stones down here and you get to the flatter gradient, it deposits all those stones, and then you stop them. So what happens is, instead of having a circular cross-section of flow, what you've got is all your stones down here, and then this is rougher.
Right.
So your capacity is reduced phenomenally.
Yes.
So if your thing is half full of silt,
Yes.
then you'll only get a quarter of the amount of water you will get through there, not half the amount.
And your suggestion to our team is always to put these onto a Google Earth.
If you can put this on a Google Earth, and then you can superimpose this line on it,
Yes.
and then you can have little inserts of the particular critical places.
To show your client that you've understood this is a 1 in 46 fall, that's a 1 in 50 fall.
Yeah.
That's a 1 in 64, so it's getting flatter.
Flatter.
1 in 94, 1 in 228, so it's getting
Yes.
flatter and flatter, and so the velocity, but
Reduces.
reduces. So the velocity over here is,
Here it's only 1.52 meters a second.
and up here,
It's 2.3. It's 3.38 meters per second.
so actually the velocity of the orange is halves, even
It's less than half.
less than half by the time it's got to the end. And did you check the friction coefficient of the liner that we're putting in?
No, I just did it with the existing pipe.
Oh, with the existing pipe, because
So it'll be slightly higher with
with the PVC.
yes.
Uncle Alistair, thank you, sir. It's always great sitting at the feet of a master. Thank you. We'll keep on feeding you cappuccinos all day.